All right, hey everybody. In this video, we're looking at how we can use the conjugate roots theorem to solve some equations, and there's somewhat of a contrived setup. Here we have a quartic polynomial, and we are also told that 2 plus the square root of 13 is one of the solutions. And where we're headed is working towards being able to solve this polynomial without being given any solutions. But for right now, we're going to take that hint and we're going to solve it a little bit quicker, a little bit more strategically. And here's what we should know, and it's going to help us develop the process that we use to get through this. If we know that we have a quartic polynomial, degree 4, then we know we're expecting 4 solutions. And they could be messy. Case in point, 2 plus the square root of 13 is one of them. It's not particularly nice. If that's the case, then we should also expect that this polynomial, which is, of course, equal to 0, should factor into 4 factors, and each one of them would be x minus one of the answers. Now, using that logic alone, we should be able to write out at least 2 of them. Like, we know that we're going to have x minus, and then this 2 plus root 13. And then a second one should be related to this conjugate. So we're going to use the conjugate root theorem, or specifically the irrational conjugate root theorem, to say that 2 minus root 13 is also one of the solutions. And that means I can write a second one as x minus, now the 2 minus root 13. And what I won't be able to do is find out what these other 2 are. Now the logic will be, if this pair of linear factors can be multiplied, we just did that in the last video, and we can come up with an x squared and a bunch of other terms, and this set of factors can multiply into ideally an x, they're linear factors, so 2 of them makes an x squared and a bunch of other terms. Then what we really have is this whole mess of a problem. Let's call this P. P is equal to, let's go factor 1 times factor 2, or the multiple, the completely expanded polynomial P that we start with can be broken down into purple times pink. And if I was able to get what this is actually equal to, I could take that original polynomial P and then divide by it, and it should give me the pink one. And once I have that, I would be able to hopefully factor it and get what these last 2 answers are. So there's a lot of drawing, a lot of logic. Here's what we're actually going to do. And here's what we can do. We can expand, and I will do this in the same color. We can expand this. Okay, I will start by simplifying those negatives, or distributing the negatives through. And then this would fall under what we did in the last video. So let's go ahead and do that. Let's expand. And if as we expand, we kind of create our columns, combine our like terms, cancel out terms that are opposites of one another, just like we did in the last video, and simplify our roots. If I have the square root of 13 times the square root of 13, that's going to be either 13 squared or 169 inside the root, and that's just going to simplify to a minus 13. Like you've seen me do before, I'm going to put the minus 13 here, kind of cross it out over here, and that's going to give us, for those first two parentheses, the two that we wrote in green at the beginning, they expand to x squared minus 4x and then minus 9 when I add positive 4 and negative 13. So if our task is to factor the original problem so that we get our 4 answers, we can divide the original problem by this trinomial we just got in purple, and it should give us a quadratic that represents the last two unknowns. So I'm going to try to write it out that way. If I divide my original problem, 3x to the fourth minus x cubed minus 75x squared minus 83x plus 36 by x squared minus 4x minus 9, then whatever I get is going to have an x squared in it. Probably going to have, actually, if I'm looking at my first step, a 3x squared in it, but that will be equivalent to these two, and it will contain my last two answers out of the 4 that we're expecting. Remember, we have the 2 plus root 13 given to us. We have the 2 minus root 13 that we got like really, really quick using the conjugate root theorem. And now the last two will be buried in whatever this pink quotient ends up being. One other thing we should be expecting is we should expect the remainder to be 0. So let's go ahead and do our long division. This is another thing that we have done in the past, so I'm not going to explain every single step of it, but I'll start us out. So we always ask ourselves, what do we multiply x squared by to get 3x to the fourth? We need to multiply the 1 in 1x squared by 3. So I'll put a 3 up here, which I kind of already did. And I need to multiply the x squared by x squared to produce an x to the fourth. And once I get the 3x squared, I'm going to multiply this by all 3 of the terms and write them underneath here. So 3x squared times x squared gives me 3x to the fourth. 3x squared times negative 4x is negative 12x cubed. And 3x squared times negative 9 should be a negative 27x squared. And I recommended that as you subtract these, you just be extremely intentional about making sure that we do the opposite. Like when we subtract, we need to do the opposite. The very first one should go away. They should be opposites. We designed it that way. And now we subtract, or now we can add because we changed the signs. Negative x cubed, positive 12x cubed is 11x cubed. And then 75, negative 75 plus 27 is going to be a negative 48x squared. We'll bring the next term or terms down and kind of continue that whole process, which I will do now. And as we get down to the end, when I switch my signs and try to subtract, I do get a remainder of 0, which is what I expected. The important thing to take away from this is that the pink quotient that we just wrote out should be, or should give us what these last two parentheses end up being. And we can achieve that by factoring it. So I will take that down, recopy and factor. And in order to factor this, I'm going to use reverse FOIL. I'm going to want a positive 11x in the middle. And I know that 3 times 4 is going to give me a 12. So again, factors of 3 and then factors of -4. If you want to do it the longer way, use that AC Bustin B method. You can use the grouping method, whichever works for you. But you get those two parentheses. And because they are the last two parentheses in my fully factored quartic, they should tell me what my overall answers are. Setting each one individually equal to 0, like we have in the past, we get x is -4 and x is equal to 1/3. So if we really wanted to, we could write 3x minus 1 and x plus 4 up here. We don't have to. The goal of this was to solve the equation, and now we have the 4 answers that we need. We have, and maybe we should write out, that they are 2 plus root 13 given to us at the beginning of the problem. The 2 minus root 13, which we can write out like that, which we figured out using the conjugate root theorem. I can also combine both of those into the same expression, 2 plus or minus root 13. And then we also have a 1/3 and a -4. This absolutely falls into the category of we're not doing any new operations, no new procedures here. We're just stringing multiple old ones together. So what should you do in a problem like this? Well, our first step is to recognize what's going on. Once we know that this quartic polynomial should break up into a lot of factors, this may go on in the back of our head. We don't have to write it every time. But we should recognize that we can use the conjugate root theorems to get extra answers, use the given and the extra answers to come up with a quadratic just by expanding, and then divide the original problem by that quadratic to come up with the leftovers, where our last two answers are hidden. Factoring becomes important again, and it's important to write your answer out at the end of a problem. This will be extendable to complex answers, and our answers may not be able to be obtained using factoring. But once we get to a quadratic, we know we at least have the quadratic formula if we're ever in a pinch. You should have enough information to be able to get this down to a quadratic that is then solvable. So with that, I'll turn you loose. Head back, try a couple of examples on your own, and use this screen or use your work from this to kind of guide you.